Hi, the study of single degree of freedom system is central in structural dynamics. The question now is it possible for a given structure to reduce it to a 1 degree of freedom system? And if so, how do you compute the equivalent parameters? And in which frequency band is this approximation valid? So let's take the example of the portal frame, where we saw that the rigid floor can be represented by a mass and the flexible column by a stiffness. The question is, of course, what is the numerical value of this equivalent stiffness? What is the value of the equivalent mass? And to which extent is this approximation acceptable? So, meaning what is the frequency band in which you can use this simplified model. For equivalent stiffness computation, the general principle is if we consider a body with arbitrary shape, a flexible body, and we have a mass hanging from it, we have the direction of motion here of the system. We can replace the mass by a force applied at the location of the mass and in the direction of excitation and motion of the mass. By doing that, we can compute what is the resulting displacement, and the equivalent stiffness will be given by the ratio of the force applied by the resulting displacement. Let's take the example of a bar in traction. So you see here that the mass is hanging from the bar and the direction of excitation is vertical. We therefore replace the mass by a force and we will compute what is the value of the displacement. So using resistance of material, we know that the axial stress is uniform over the area and is given by the Young's modulus multiplied by the longitudinal strain, which is du over dx. By integrating this uniform stress on the surface, we find the normal force and see here the area of the section. Then, using static equilibrium at the tip of the bar, we know that the normal force must be equal to the applied force. And by integrating, we get u of x is fx over ea, where the constant after integration is 0 because u is 0 at 0. We can now look at what is the value of d by replacing x by l. So we have d is equal to f L over EA, so that F over D is equal to K, which is EA over L. We see that the stiffness is now proportional to the Young's modulus and the area, and inversely proportional to the length. Now, if the direction of motion is horizontal rather than vertical, then it is not anymore a bar in traction, but it's a beam in bending. For that, we could use the formulas of resistance of materials or just go to existing tables. In this example, the maximum displacement at the location of the force for a cantilever beam is given by PL cube over 3EI, so that P over delta is equal to 3EI over L cube. We see again that the equivalent stiffness is proportional to the Young's modulus of the beam, its inertia, but also inversely proportional to L to the power of 3 in this case. So these equivalent stiffnesses for beams can be computed using formulas from resistant materials or using tables. So this is the kind of tables for a cantilever beam. You can find them for different boundary conditions, such as here simply supported beams. Now we move to the example of the portal frame. So here we have a mass that is supported by two columns, and if we divide the problem in two, we see that it's equivalent to applying F over 2 to one of the columns. So this is not strictly a cantilever beam because at the other end here it is guided so that the rotation is 0. For that you can also find tables. So here you see a cantilever beam with a guided end and a load applied, and it says that the maximum displacement at the tip of the cantilever beam is PL cube over 12EI. So because we have two columns, the total stiffness will be 24EI over L cube. The equivalent mass is the mass of the floor, so that the first natural frequency is given by 1 over 2 pi square root of 24EI over L cube m floor. So you see that we can find with a pretty simple formula the first natural frequency of our portal frame. Now for the equivalent mass, we are usually going to use equivalent kinetic energy method, where we know that the kinetic energy of the equivalent system is 1/2 its mass times the velocity squared. Now if we consider, for example, the mass on a spring, and we now consider the spring has some mass, we would like to replace the mass of the spring by an equivalent mass at the location of the initial mass m. So we will add an additional mass ma, and the question is, what is the value of this additional mass? So we have to look at the velocity profile along the spring. So obviously it's 0 at this location. It will be maximum, so it will be v at position L at the end. And between the two, we assume that the profile is linear, so it is given by this expression. The density here is the linear density, is the mass of the spring divided by its length. Now we can just compute the kinetic energy of the spring by integrating from 0 to L 1/2 times rho times the velocity squared, which is given here. And if we perform this integration, we see that we end up with simplification here to 1/2 ms3 VL squared. So this is actually showing that this additional mass is ms over 3. So only 1/3 of the mass actually has to be put at the tip here to represent the mass, the full mass of the spring in the system, and have the same kinetic energy. You can do exactly the same for the bar in traction, where actually the displacement, you know that the static displacement is Fx over Ea. You assume again that the velocity is a linear and starting from 0 here and ending with v at position L. And by integration, you get 1/2 rho Al over 3 times VL squared. This is again the additional mass, and note that rho Al is the total mass of the bar, so it's again 1/3 of the mass of the bar in traction. Now it is not always 1/3, but in this sample example it is. Now let's discuss the limits of the approximation. So we have seen that if we have a mass hanging from a bar in traction, we can replace it by an equivalent stiffness, that is Ea over L, and the mass hanging from it. But we could also use a second model where we have an additional mass which is 1/3 of the mass of this bar, which has been neglected in the first model. Now, using finite elements, we can also compute the exact response. So first of all, let's look at the natural frequency. So if we assume that we have no additional mass, we have k is equal to E over L, and the mass is 100 kilo, and we end up with a natural frequency of 145.87 Hertz. If we use the additional mass in this case, you will find that you have 1 additional kilo compared to the 100 kilo. So it's quite negligible, and as you see, the natural frequency is very close. So when you plot the response of these two systems, you see that indeed you have a slight shift, but this is not very big when you look at the big picture of the natural frequency. Now for these models 1 and 2, we also added the exact solution which was computed with finite elements. And what you find in that, in the finite element model, of course we know that the continuous bar has an infinity of mode shapes, and so they come also into the picture. And you see that here you have one extra mode coming at that frequency. So if you are using the equivalent model of Wandorf system with equivalent mass and stiffness, it will be valid for frequencies which are smaller than 2000 Hertz. Let's assume now that the mass of the bar is multiplied by 10. Now the additional mass is not 1 kilo anymore, but 10 kilos, and so you see that there starts to be a significant difference between the natural frequencies, which is somehow visible here on the graph, and even more if you zoom. But what you also see is that because the mass of this bar is higher, its natural frequencies will be lower, and so they interact at much lower frequencies with the main dynamics of the system at low frequency. So in this case, you see now that the single degree of freedom hypothesis is not valid for frequencies higher than 500 Hz. As we saw, in some cases, the rigid elements in a structure can be replaced by a mass, and the flexible elements by an equivalent stiffness. But there are some structures where it is not possible to make such an approximation. But as we will see, it is still possible to reduce the system to a 1 degree of freedom using the single mode approximation. So we consider this beam, which is of length L and simply supported in this example, and the displacement W of x and t, where x is the coordinate along the beam, is supposed to be decomposed into two functions, one function of time eta of t and one function of space f of x. Then we would like eta of t to represent the displacement at a reference point x is equal to eta, marked here on the figure, and we choose f of x as the ith mode shape of the beam, which is normalized such as this function is 1 at position x equal eta, which ensures that then the displacement is w of x and t is equal to eta of time, because f of x is equal to 1. So that means we have to choose f of x is equal to psi I, so the ith mode, divided by the value of the ith modes at the position eta. Now with this assumption, we can compute the strain energy, which for a beam is given by 1/2 the integral over the length of the beam of EI, the bending stiffness, times the second derivative of the displacement squared. And if we isolate the part that depends on time, we get this second integral, so that the strain energy can be written as 1/2 times an equivalent stiffness times a displacement squared. So this equivalent stiffness is given by this integral, and we can define a non-dimensional factor here, which we multiply by EI over L cubed, which has a value of stiffness. For the kinetic energy, the definition is 1/2 the integral over the length of rho times the velocity square on all points of the beam. We again take the parts that depend on time outside of the integral, and that allows us to define an equivalent mass m tilde, which is given by this expression, this integral expression, and which can be given also by a non-dimensional factor psi of m times rho L, which is the mass of the beam. In the same way, we can compute the work of external forces, which is the integral of these forces times the displacement over the length of the beam, and taking out eta of t, we get an equivalent force given by this, and the equivalent force also can be defined by a factor phi L times the total force PL. Now this means that now the problem can be written just in terms of the displacement of the point we have chosen on the beam, so the eta, with an equivalent mass m tilde and an equivalent stiffness k tilde and an equivalent force p tilde. This is the definition of K, M, and P, so they are given by these three factors, which you can find if, for example, you are considering the first mode of a beam. You can find in this book here tables where, depending on the boundary conditions, you have the values of the different factors giving the equivalent stiffness, mass, and loads. So as an example, if you consider simply supported beams, beam with a point force in the center. You see that K and M are given by this, where the factors are for the stiffness 48.7 and for the mass 0.5. If you use these factors in the equations, this is also the load factor, which is given by 1, and represent the transfer function, you see that for a full model of a beam you would have several modes, so you will get the gray curve, whereas for the reduced equivalent 1-DOF system you have the orange curve, which fits perfectly the gray curve around the first mode. So we now consider the case where the beam would be modeled by finite elements, in which case it would result in discrete equations with matrices M, C, and K, and so this covers also the case of a general end-of system. We assume that the displacement x is written as only the multiplication of a modal amplitude of the mode we chose and the mode shape we chose. So we use a single mode for the approximation. We then replace in the equation and pre-multiply by psi I of t, and we obtain a single equation of this type with the modal masses, the natural frequencies, and the modal damping. Now we take here the particular case of a point load at this reference position. So we choose a reference position on the beam as we did before for the continuous system. And we know that the displacement at this reference position is given by the following equation. So we will now replace in this equation Zi by x of eta divided by psi I of eta. And we replace Fi by this expression and then divide by psi I of eta. So if we do that, we obtain the following expression, which is now expressed as a function not anymore of the modal displacements, but of the displacement of the reference point we have chosen. This means that the mass, so these factors here, are dependent on the position on the beam eta, and so we can define equivalent mass, equivalent damping, and equivalent stiffness, which are then a function of the position we chose on the beam eta. Now, what is the link with what we did before for continuous systems? Well, you see that if I take psi I of eta is equal to 1, then x of eta is equal to zi of t. So the modal displacement of the single mode corresponds to the physical displacement, which is what we did with the continuous system. Now, in this case, if this is 1 on the denominator, then m equivalent is the modal mass, and for continuous system, this equivalent mass was given by the integral of rho f squared, which is also the modal mass for continuous systems. For C, we did not define a damping for the continuous system, but for K, we have again the fact that now we have the modal stiffness mu I omega I squared, which is equal to this equivalent K we defined for continuous systems. Now, this is an example of a complex finite element model of a building. You see that the first step consists then in computing mode shapes, which are represented here. They are mass normalized, so the mu I is equal to 1 in this case. And then we want to reduce at a specific point on this building to a single degree of freedom system. So you see that for that, we need the different quantities, the mu I and the psi I, so at the location where we do the reduction. So we choose on the building one reference point here close to the top in one specific direction, which gives us then the value of mode shapes in this direction at this location. Based on that, we are able to then determine for this mode shape, the first mode shape, the equivalent mass, stiffness, and damping coefficient. And by applying a force, we can compute the transfer function between the force applied and the displacement then in this horizontal direction, which is done here. And you see again that the full model, of course, includes several mode shapes, so it has several peaks and it's the gray curve, whereas the orange curve represents the equivalent SDOF, which again fits very well in the frequency band around the first natural frequency of the building.
In this video, we have seen that whatever the complexity of a structure, it's always possible to reduce it to a single degree of freedom system approximation with an equivalent stiffness, mass and damping. But always keep in mind that this approximation is only valid in a given frequency band.